Hello everyone. Good morning. Uh, Welcome to all of you in my session. In this session, I'm going to discuss the topic of axial dispersion, which is the next topic of the modeling parameters. Already, I have discussed complete segregation model and tank in series model here on this my channel, and today I'm going to discuss about the axial dispersion model. So let's try to understand the axial dispersion model. Okay. Yeah. So, my dear student, you can see uh, the importance of this model becomes very important when we talk about the plug flow reactor also. So, this model is also valid for plug flow reactor. First of all, plug flow reactor. When we talk about, my dear student, ideal PFR, there we assume that there is no axial mixing possible in ideal PFR. No ideal mixing is possible in case of ideal PFR. Okay, that becomes very important. But whenever we talk about, my dear friend, reality, in the real case, there is no such things occur, in PFR also. So when we talk about the real case, when we talk about real case, there will be some non-ideality that will get arises. Okay, so real case is non-ideal reactor. Okay. So whenever we talk about the real case, that is non-ideal reactor, as like when we talk about non-ideal gas, so non-ideal gas also exist in the nature that is the actual real gas. So okay, so at a particular condition, a real gas becomes ideal gas. Okay, so here also at a particular condition, a real ideal, a real reactor will becomes ideal reactor, and the assumption is no ideal mixing is possible. Then that will make the real reactor as an ideal reactor. So here again, in real case, the reactor will be called as non-ideal reactor, and here there will be an axial dispersion will be possible. Axial dispersion or axial mixing is there. Axial dispersion and axial mixing is there, my dear friend. So whenever there is an axial mixing, that axial mixing, term encountered by a term that is called the axial dispersion coefficient. Okay, so definitely you'll have to add some terms over there, and that term is called as the axial dispersion coefficient. Are you getting what I want to discuss over here? There is term that you will see in the derivation. There will be an axial dispersion coefficient. Okay, so it is same as like diffusion coefficient, and also it's follow fixed law of diffusion. So same as diffusion coefficient, and it will also follow fixed law of diffusion. Are you getting fixed law of? It will also follow fixed law of diffusion. So I think up to this, it's very clear. Whenever we talk about the real reactor, this is the case of non-ideal reactor, and in non-ideal reactor, axial dispersion will be there. In case of PFR also, I am only talking about PFR, okay, not talking about MFR, because this model is valid for PFR, okay, PFR. So axial dispersion coefficient will be there, okay, and that axial dispersion coefficient behaves like the same. The axial dispersion coefficient is same like your diffusion coefficient, and it will also follow my dear friend fixed law of diffusion. I think up to this everyone is clear now. Now coming to the next point, how it is behaving like. So, my dear friend, when we talk about plug flow reactor, the case of plug flow reactor is profile of plug flow reactor is like this. It is thoroughly flat profile. Okay, this is thoroughly flat profile. It is ideal PFR, but in reality, what will happen? There will be some dispersion will be there. Are you getting? So here you can say the profile should be like this, but in real case, it does not look like this. So there will be an axial dispersion like this, and it is called axial dispersion. Are you getting? This is axial dispersion. Okay. Now, how this axial dispersion term will be, encountered in the mathematics. That is the objective of this session, and I will let you know later how we are going to encounter this axial dispersion term and how, our PFR get deviated from, ideality due to this axial dispersion. So, just try to understand one thing. I'm starting this the mathematical modeling of this part actually. So I am assuming this is backflow profile. Okay. So here molar flow rate of tracer will be entering Fa at Z, and here I am assuming a small thickness dz. Okay, and here it will be leaving at Fa. Okay, at Z plus dz. Okay, and it is bulk flow. And here it will show bulk flow because there will be two flow will be there, bulk flow and migration. One another flow that will be there here, that is dispersive flow, that already I have told you, back because due to dispersion. So that terms will become also important in case of non-ideal reactor, and which is absence in case of ideal reactor. So here, so it will be like this. Here it is dispersion. So this term will also come in importance. So here it will be going at Na at Z, and here it will be coming Na at Z plus dz if I am assuming the thickness. Are you getting? And here it is dispersive flow. Are you getting? Because both of these two you'll have to come, considered in the model whenever you are going to model a PFR, and actually non-ideal PFR. So here the unit of this particular thing is mole per second because it is molar flow rate, and here when we talk about migration bulk flow, one thing I am letting you to know, bulk flow model here Fa can be determined by, volumetric flow rate into cross-sectional, concentration. So can I write Fa is equals to minus U multiplied with area, that is volumetric flow rate, and it will be multiplied with Ca. Are you getting? So as simple as that. You all have studied in, mass transfer course. So it will be very easy for you to understand the thing. So it is bulk flow. This term signifies bulk flow. And already I have told you that this term dispersive flow will follow fixed law of diffusion. So can I write Na, that is equals to my adjustment Na multiplied with A, that is flux. So that is equals to my adjustment minus dA dCA by dz and multiplied with area. Are you getting? You can understand these things from here. So we have calculated both of the things. Now coming to the next. Now apply for the tracer balance. Okay. When we apply the tracer balance here, you can understand the thing. From this particular cross-sectional area, what will happen? Concentration multiplied with A multiplied with U at Z here, and here This is bulk flow. Again, I'm writing here. There will be two flow over here. No? One is bulk flow and one is dispersive flow. Okay. So here it is CAU and cross sectional area, and here my dear student NA bar at Z, and here it is at Z, and here it will be coming CAU at Z plus DZ, and here one more NA bar at Z plus DZ. Are you getting? Both of these two things will get coupled when I will be doing the modeling of this PFR. Now coming here, what happens over here? So can I write my notation FA at Z plus an A bar at Z? Are you getting? That is stressor in minus FA at Z plus DZ. Are you getting? Minus an A bar at Z plus DZ. That is out. In minus out. Okay. And that is equals to accumulation. So d upon dt of CA, okay, and dz in minus out, that is equals to, this is simple mole balance over here that I have used. Okay, so can I write FA at Z plus NA bar at Z, okay, and I'm just dividing this term by dz. Are you getting? Minus FA at Z plus dz minus NA bar at Z plus dz divided by dz, that is equals to A and dc by dt, and here dz term I have divided, so it will come like this. Okay, so again can I write here minus dfa by dz minus dna bar upon dz. This is just the simple differential, that is equals to A dc by dt, A dc by dt. Now, so again here can I write FA, that is equals to C and UA. This is bulk flow. So can I write here minus AU dc by dz plus d del 2 Ca upon del Z2, that is fixed law of diffusion that will follow, multiplied with area, that is equal to A dc by dt. Are you getting? So can I say this A and this A will get cancelled out. Finally, you will be getting a derivation U dc by dz plus d del 2 Ca upon del Z2, that is equals to my descent del C upon del T. It's a very important relation, and this relation is called equation for dispersion model. Equation for axial dispersion model. Now, what you can elaborate from this particular equation. So here you can see this is term of bulk flow. This term signifies the diffusive flow in a steady state, unsteady state condition. Are you getting? So when we will change in dimensionless parameter, why we change in dimensionless parameter? Because the thing will become very easy for you to understand or remember. So can I write here Ca star, that is equals to Ca upon Ca naught. Okay, Ca star is equal to Ca upon Cn. Here you can write this concentration as Ca also, because it will become very easy for you to understand. Okay, Ca del Ca. Here you can write Ca. Here it is Ca. If a reaction is happening from A to B, okay, that's why. And Z star, that is equals to Z upon L, where L is length of P of R. Throughout the length it will cover, na? So if it will be our P of R, so this length should be there to cover this particular reaction to throughout the reaction. So, and can I write time, that is equals to L upon U, length of P of R upon velocity of the substance coming. So can I write my reaction minus U Ca naught upon L and del Ca star upon del Z star plus d Ca naught upon L del 2 Ca star upon del Z star, that is equals to U Ca naught upon L and del Ca star upon del T. Only I have put all these things over here. I am not doing any new things. That now finally you can write this term minus Ca naught del Ca star upon del Z star plus dE upon UL, and you can write del 2 Ca star upon del Z star, that is equals to del Ca star upon del V. Okay. Finally, you will be getting this particular term. This particular term. In terms of dimensionless parameters. So my dear student, you can see there is term over here dE upon UL. The term dE upon UL. Okay, that is called as dispersion number, very important number. That's why we have put into in the form of dimensionless parameter, and that is equals to transport of tracer due to dispersive flow divided by transport of tracer due to bulk flow. Are you getting? Now, what you can deduce from here, my dear friend, if dispersion number exists, then what will happen? The reactor will be non-ideal reactor. Are you getting? Because here the dispersive flow is also coming in, in account, so that the reactor will become non-ideal. So if you want to check whether the reactor is ideal or non-ideal reactor, you just go for calculation of dispersion number if it is going to exist. And this shows the significance of dispersion number is the transport of tracer due to dispersive flow and upon transport of tracer due to bulk flow. You can see here D signify the dispersion and U and in multiplied with L signify the axial flow, that is bulk flow. Okay, bulk flow, sorry. Now, so I can define dispersion number is a measure of relative importance of transport of tracer due to the dispersive flow and to the over the bulk flow. Okay, so you can define the dispersion number here also. It shows the relative importance of tracer, relative importance of transfer of tracer. It will become important. transfer of pressure due to dispersive flow over bulk flow. Okay, I think the definition part is very clear to all of you. And my dear friend, it's very important definition and it's very important parameter. Most of the interviewer I try to trap you while asking all these things. Okay, so dispersion numbers. Most of the students used to leave this particular part, but no, this part is not very tough. Already I am you know trying my best to let you understand this part exactly. Okay, for the non-ideal lecture. Now coming to the next part, it's very important. If this person number is equals to zero, what does it mean? That means transport of pressure due to dispersive flow will be equals to zero. Are you getting? Transport of pressure due to dispersive flow is equals to zero. Okay, and or you can like flow is only due to bulk flow term. Are you getting? These two things can come into account whenever dispersive flow is zero. Sorry, dispersion number is zero. So this will signify the case of when dispersion number is zero, it will signify the ideal plug flow reactor. Ideal plug flow reactor. No, in non-ideal plug flow reactor, dispersion number will be there. So don't get confused here. So if they will be asking what if dispersion number is zero, then you'll have to understand that you have to say that ideal. This will be the case of ideal plug flow reactor. And when my dear friend, dispersion number that is equals to infinity. So what will happen? Transport of pressure is due to only dispersive flow. Transport of pressure is only due to dispersive flow. And what does it signify? It does signify it is the case of ideal CSTR. Okay, it's a very important point that you have to keep in your mind whenever you are going to give your interview in any public sector and in any company. Okay, so now one more important factor that has been left in this session is that is backlet number, and that is equals to 1 upon dispersion number. So you can write backlet number, that is transport due to bulk flow divided by transport due to dispersive flow. Are you getting? Transport due to bulk flow divided by transport due to dispersive flow. Now, so if backlet number is zero, then what does it signify? It will signify it is the case of ideal CSTR. And if backlet number is infinity, what does it signify? It will justify that it is the case of ideal PFR. So these are the some basics parameters that you need to keep in your mind whenever you are trying to solve the axial dispersion model. Okay, so hope I have tried my best to let you understand the topic, and hope you understood the topic all as well. So if you're facing any doubt, you just put your doubt on the comment. I will always be ready to give your answer. And whenever you are trying to solve the problem, just go through this video first. And after watching this video, definitely, I hope you will get some good insight on this particular model. Okay. Okay. Thank you, and thank you all for watching.